everyone. Once again, welcome back to the day 4. After the session, we will resume the session after the tea break. Please continue.
Yeah. So it's 3:54. I roughly have around 35 minutes of time. Okay, so we stopped at the small signal model. Right? I don't need mic, right?
No.
No, mic is a problem. Okay, so I replaced the entire converter with a small signal model. Rest everything remains the same.
But recording is going on, sir. If you have mic there.
Oh, yeah. Okay. So you understood the idea with which I derived the small signal model, right? Okay. So the rest business is the same. Again, you take the reference, you have the actual, then there is a compensator, and this is what don't have to worry right now. This is called a pulse width modulator because this is also a very nice interview question for PG students who are looking for careers in power electronics and associated, if in case you want to switch to power electronics EEs. We have V0 is equal to D into Vg, right? What is the range of D? 0 to 1. D cannot be greater than 1. D is between 0 to 1. So if D is 0.5, half of Vg. 0.75, 3/4 of Vg. Is this clear? But this D in real time is not like this. It's not a number. It is a pulse. Because you turn on the MOS switch or you turn on the switch. So what does D tells us the average of this? The average value of this pulse is this D. If D is 0.5, it means on for 50%, off for 50%. If D is 0.75, on for 3/4, off for quarter. That's what it means. So this is the one which converts. Pulse width modulator is the one which converts this D, which is in the form of numbers, to pulse. That much is enough for today, not more. And that is modeled as 1 by Vm. Let's not go too much in detail. Let's assume this because not everything can be dealt with at a time. What is important is a small signal model. So we have replaced the entire converter with a small signal model. Is that clear? Okay. This converter is replaced, which are switches, which has too many things, not diodes and all, right? Is replaced with a small signal model. This is how it is. I have even simplified this converter, right? This converter I have replaced with something like this. What is it? Is you have the reference, you have the actual voltage, you have the compensator, pulse width modulator that will give you duty cycle. Now we saw the transfer function, right? You want V0, correct? You want V as the output and you have duty cycle. The transfer function is GVD. This is from here, right? Output voltage is transfer function GVD into duty cycle. I taught you this, right? The same thing I have put here. So we have duty cycle, right? This is what it is. We have the duty cycle. We want output voltage. The ratio of V0 by Vg is, we call it as GVD. Okay? The ratio of V0 by Vd is GVD. Okay? Because I have duty cycle, I want output, so the ratio of that is GVD. Similarly, we have input Vg, the ratio is GVG. We have I load as the input, the ratio is Z out. It is the same thing what we put here. Is that clear? The ratio of V by D is GVD, the ratio of V by Vg is Vg, the ratio of V by I load is Z out. The same thing is put. Any doubts here? So what are we trying to do is we are trying to simplify things. It was this complex. We made it simple like this, where we can apply linear analysis techniques, and then I made it even more simple. You got it, right? Now this, once you get into this form, whatever you have studied in your 5th semester class on linear control theory is what you can apply. Because it is on this form. This is a forward path, this is a loop. Right? Now you see, now onwards, I am not talking anything hi-fi, nor did we talk before also. But you can see all that you have studied in controls is going to come. Right? Now, if I give you a block diagram like this and ask you to calculate V by V reference, how will you do? Okay, let's look at one thing and let's go to the other. Right. You know, recently we had a very nice interview session with all the great star words in power electronics, but they asked us this question. G of S, this is the output. This is what V reference is. This is H. And this is the error. So what I am trying to do is, this entire thing, GC, forget about the existence of this. What did I tell transfer function? If I am trying to plot transfer function of V by V reference, I should not consider VG and I load. They are 0. So these are not existing to me. Though it looks complex, assume they are all 0. Only the block diagram is this. Only this much. So the entire GC, 1 by VM, GVD, I have just modeled as G. Is that clear? And the H of S is as it is. So if I want V naught by V reference, can someone tell me what is V naught by V reference? Look at this. G by 1 plus GH. As simple as that. Now look at it. V, forget about these two. Okay? V by V reference. V by V reference is G. What is G? Whatever is in the forward path. What all there in the forward path? G of S, 1 by VM, GVD. Right? GC, GVD, 1 by VM. It's the same. Divided by 1 plus GC, GVD by VM into H. Simple. Right? Now, if I want V by VGS, okay? V by VGS, I want this. What I want is the forward path here. So this becomes GVG. Look. So this is GVG. If you look at, this becomes GVG, only GVG. Divided by 1 plus GH. Similarly is for ILOAD. So everything is what you already know. We just have to translate it to this form. Now, let's look at this G into H is the hero of the next session. So this guy is important. Now I will call this guy as T. G by 1 plus T. This is called as the gain, this is called as a loop transfer function or open loop transfer function. Now this guy, you remember I made a statement here that I am going to design GC such that it can account for variation in VG, it can account for variation in ILOAD. I made the statement, do you remember this? And I told you, without having any feedback from VG or ILOAD, this compensator is to be designed. Now that happens only by designing this T. This T has the information of VG and ILOAD. Now if you can design T well, you can design a best control system. So the approach starts from here. So I am going to tell you why this T is required. You got it? Now what we will do for now is, I will replace this by T. H, GC, GVD by VM, which is common on all the cases, correct? Here, here and here. So they are just replaced by T. And all the now in the numerator, one modification I have done is, I have multiplied and divided by H. Here, I have multiplied and divided by H. Because if I multiply by H, this becomes same as this. Correct? I have an H here. And this is T, correct? I will replace this by T. T here. Now, if I multiply with H here, this also becomes T. So I have to divide by H. So 1 by H into T by 1 plus T. That is just to simplify it, there is no business there. And the rest I have kept it as GVG by 1 plus T, Z dot by 1 plus T. Is that clear? Shall we proceed? Okay. Okay. Now let's look at this. How is that? I am trying to make sure that any variations in VG should not be transmitted to V0. Very important. I have V by VG, which is given by G VG by 1 plus T. Correct? Okay. Now what is this? This is a small signal model. I replace, see, if I write capital V, it is the output voltage. If I write it as V cap, it is the disturbance in the output voltage. Okay, because I am looking at small signal model. So if I write Vg, it is the actual input voltage. If I write Vg cap, it is the disturbance in the input voltage. Okay, you understand this? Disturbance in output voltage, disturbance in input voltage. Okay, now what does this ratio tell? Okay, what is the disturbance that is propagated to output voltage? What is the disturbance or what is the effect on the output voltage due to disturbance in input voltage? That is what you say, right? If I say this ratio is very, very high, what it means? What it means? Any disturbance in input is transmitted to output because this ratio is high. Right? Now if I say this ratio is 0, what it means? Any disturbance in input is not transmitted to output. Correct? The ratio is 0. So now you tell me, look at this. Do you want this ratio to be high or low?
Low.
Low, correct? Okay. Very good. If you understand this, then you are a control expert. Now this is that equation. Now if I want to make this very small, tell me what should I do here? Which parameter would you like to make it high? T, correct? Correct. So your T should be very, very high. Always remember this. Your loop gain should be very high. Your loop gain should be very high for small frequencies or for large frequencies? Small frequencies. So you will see in the plot that first thing is your T of S should be very high at low frequencies. If you can do this, then you have regulated, because that is what we want. The entire job or the hands-on what we do, let's see if the time permits, we will make sure that this loop gain is high, or at least I will make sure you will be able to plot this loop gain and see that the loop gain is high. Let's see that. Okay. Now that is one thing. Second thing is, now this is the next transfer function, V by V reference. V by V reference is this. V by V reference. So whatever you get, what change in V reference changes V. That is what V by V reference. Now let's see what happens. Now that you have made that the T is high, okay, T is very high. So what happens to T by 1 plus T when T is very, very high? T is a very large number. Divide that by 1 plus T. What happens to this?
Less.
No. What happens to this entire number?
Less than
1. Let's say T is 1000 divided by 1001. 1 you can neglect in front of 1000. So this gets cancelled. So what you get is V by V reference is only dependent on H of S. That means whatever you change here will get changed here, only dependent on this. It is independent of any disturbances that is seen here. Let's say there is any disturbance here or here, your output is not affected. It is only dependent on the sensor gain, and that is what you want. Let's say you want to regulate it to 13.3 volts. Let's say due to some disturbance this becomes 13.2. Do you want to detect the change or not? Yes, you want to detect the change, because only if you can detect the change, something can be controlled here. Let's say it is 13.3, it has gone to 14 and your sensor is not able to detect it. What do you think? You think that still output voltage is 13 and then you don't take any correction factors, correct? So you want your output to be very sensitive to variations in V reference, and that should be dependent only on sensor and not on any of this. That's what is automatically happening, right? You get that? Is that clear? It's just dependent on the sensor. Okay. Now, so now that you have learned about T and what is the basic characteristics of T, how should T look like? T should be very high at low frequencies, correct? Because my disturbance is low frequency, otherwise the entire disturbance from the input gets transmitted to output. Is that clear? That is a very basic characteristic. So whenever you look at T or the loop, first thing you should look at is whether its gain is very high at low frequencies. Is that clear? Okay. Now, there are two things that is very important. First, let's not worry about how did we draw this, but let's look at whether this is satisfied, that whether T is high at low frequencies. Can you look at this? Where is low frequency? Here. This is low frequency. These are all high frequency. See, I am not bothered about high frequency because my filtering can take care of high frequencies. Now look at what is happening here. It is close to how much? 60 dB, right? Can someone translate 60 dB to absolute values? Remember, I am talking about log scale, and this is 20 log. Okay? There is a reason why should you multiply by 20 all of that. Okay? This is 20 log T is 60 dB. So what should be T? Yeah? Do you 1000, right? You don't need a calculator for this. 1000. And what did happen here? This is a very large value. We were looking at V by V reference, no. V by Vg cap. This is a very large value. Something divided by very large value is very small. Correct? So what is happening is, if I approximate it as GVG by 1000, what do you understand from this equation? Any disturbance in Vg is attenuated by 1000 times. Right? Any disturbance is attenuated by 1000 times. Do you want that? Correct? Let's say the disturbance is 10 volts. Right? If you propagate, if you make this as 1, 10 volts gets passed on to your output. You will see this entire thing riding on your output voltage. But imagine this gets attenuated by 1000 times, so this becomes 10 by 1000 or becomes point, not 1. So 10 volts of disturbance is now becoming 0.01. Do you want it or not?
Yes.
Yes. That's it, you're done. Clear? Now, this is the objective. You should get something like this. So first we should see what do we have. So what is T? We have defined T here, right? T is defined here. So let's write T, because only if you write you get it in your heads, right? Okay. So what is T is, the loop is G into H is GC. Okay, let's go back here. Yeah. What is loop? GC 1 by Vm GVD into H. It's the loop. Very simple, right? So it is GC 1 by Vm GVD into H. Okay. Now you should make sure that this product is very high, almost at low frequencies. Now for that, we should look at the way it is first. Only then you can modify. Okay. Now let's identify the parts. H is the sensor transfer function, which is purely a number for me now. Correct? I have not called it as h of s. You see here, it's written as h of s, and this becomes just h. I have removed off s. The reason is, it's just a gain. I am telling you that look, the output of your sensor does not depend on the frequency that you give. It only depends on the amplitude that you give. Not just frequency and amplitude dependent, only depends on amplitude. So I have simplified it. Right? Okay. So this we already know. Do we have control over H to shape our T? No. It's your customer who gives you this. He says, look, use this filter. Or some sensor filter gives you. GVD is the ratio of V to D. How do you get it? Is you get it out of the circuit. You have to apply circuit techniques to get what is GVD. You don't have control over it. Okay? You don't have any control over this also. And this is a pulse width modulator. I told you it is going to convert your DC into this. This has a fixed amplitude. 2, 3, 4. You don't have any control. Correct? You don't have control. So what do you have control over? What is the only thing that is remaining? GC. And what is that? That's our compensator. That's the brain. So you will have to design GC such that you have very high gain at low frequencies. Is that clear? Because rest everything is fixed. You don't have control over changes in VM, over changes in GVD, or changes in H, but you only have control over GC. Is that clear? So ideally I should be shaping it like this, but I should find out whether do we have something like this naturally, or should we shape this GC such that you get a shape like this. Is that clear? And this is called the design of controls. Is designing GC such that you have T like the way you want. It is called as loop shaping techniques. That's the reason why I gave the topic called frequency response. Design of controls using frequency response, because this is a frequency response plot. The response is not based on amplitude alone, it is also based on the frequencies that you input. You input a frequency of 100 kilohertz, you get a gain of minus 40 dB. You give a frequency of 0 hertz, you get a gain as close as to 60 dB. It makes sense, an absolute sense, what frequency you input to your system, and your output responds not to just amplitude, but also on the frequency. Is that clear? So h of s that you study in your Laplace transform, 1 by s plus 3 or whatever, it has a lot of significance when it comes to physical systems, because it is telling you, look, I am not only responding for the amplitude that you provide, I am also responding to the frequencies that you are inputting. It actually works like this. If you have a very high frequency, it says I cannot give you too much of gain that you expect. Right? It's not just, it's k by s plus 3, it's not as simple as that. So Laplace transform make a lot of sense in physical sense. We use a lot of Laplace transforms in real time, and in control systems it has a lot of application. So you understand, right? So I am supposed to design GC so that I am going to shape T. Is that clear? Now, last point before we go to the, that's what is put up here, but really important. Okay. Now, last point to conclude is, this is a number, right? This is a number. This is a number. Now, before we design, we will assume this as 1. The first assumption is 1. You can't assume 0. If you assume 0, 2 loop becomes 0. Let's assume 1, and then you can multiply anything that you want with this. So what we do is, first, let's assume that the compensator is just 1. Okay, that means it does not have influence of the loop, and try to know how is this T, and that is called as uncompensated loop, generally denoted by TIU, which shows it is uncompensated. And then once you know how the loop is, once you shape it, that becomes a compensated loop, that you call it as TCU or TUC. C stands for compensated, I stands for uncompensated. Okay, so if you make GC as 1 and then you design the loop, it is uncompensated loop. Now, in the uncompensated loop, right? Okay, GC is 1, correct? VM is a number, correct? H is a number. They are all constants, correct? So they are just constants K. Now, what you left with is GVD, correct? Now, GVD, we should understand what is happening in GVD. You got it? It is a GVD which is shaping this. Your K will only decide this. K will decide only this number at 0 hertz or whatever is that below this. It only decides this number, from where should your plot start. The entire shape of your plot is actually dependent on your GVD. Okay? Now, okay, look at this network. What is the order of the, if I ask you a general question from, let's say we have a linear circuit theory class, LCD, what we call it. What is the order of the circuit? We talk of the order of a circuit, right? We define an order for a circuit. What is the order of the circuit? 2. Why? Because we have 2 energy storing elements. Okay? Now these energy storing elements are the elements which gives to dynamics. Let's say if you don't have this LNC, you had a resistor everywhere. What would you have done? You would have replaced this entire thing by an equivalent circuit. Correct? V0 is equal to some equivalent R times V in. Was there any dynamics associated? No. It would have been a simple algebraic equation to solve. And in terms of memory, there is no memory associated. What you give as input is what you get as output. There is no memory, there is no lag, there is no lead phase associated, so there is no power factor problem and all of that. Now that we have L and C with us, right? If you have to solve this equation and would like to capture the dynamics, you start writing differential equations, right? Because differential equations capture the essence of the entire network. It has the previous history. It can also predict what happens in the future, right? Now, since these 2 elements are there, these are characterized as second order system, or if you derive a differential equation out of it, it's of the second order. And then if you convert it into Laplace, the order of S is 2. I'm just telling you this in brief because we have a lot of things to do. I'm sure you know you know the reason why you have s square in the Laplace. You know it, right? It's a very simple thing. Okay. So why am I talking this is this, if you solve, if you get GVD, it will have an s square term. That means it's a second order differential equation, or in Laplace domain you have two poles. So I can write it as k into a generalized form. Okay, I can write it as GVD, right? Some constant kd divided by a general second order transfer function, which is s, which I follow this pattern. You can follow any pattern. Q into omega naught plus 1. Right? Why am I the thing is I wanted you to understand why did I write GVD as something like this? Because GVD has two energy storing elements, LNC, point number 1, and because of that the order of the transfer function will be 2, and since it's a second order transfer function, the general representation of a transfer function is something like this. It has a gain, DC gain, and then it has something like this. Is that clear? Now, see, why am I telling you these techniques is, I am trying to give you a general perspective of controllers. I have not derived any equation, but I am constructing something out of nothing. Is that clear? Now, what is the value of KD? Okay, to understand this, you should know, right? KD is called as a DC constant. Have you heard this term constant, DC term constant in a transfer function? That is when you don't have any frequencies. Okay. Now, let's say this is a transfer function. Let's say g of s. I will write it as k divided by s by omega naught plus 1. Let's say we have a transfer function like this. Now, general random transfer function. When s becomes 0, right? What do I mean by s becoming 0? S becoming 0 means I am giving only DC input. So when I make this 0, what do I get? K. That means your system behaves like a constant. And this only happens when you give DC input. That is why it is called as a DC constant. When you give some frequencies to it, depending on the frequency, the gain actually changes. Similarly is this KD. KD is when you don't pass any frequencies to your input. Okay, that is zero frequency input. What is the gain? Right? Now, to understand this is GVD, right? What is GVD? GVD is the ratio of voltage to the duty cycle, correct? And if I don't pass any frequencies, that means I am in steady state. What is the ratio of voltage to duty cycle in steady state if it's a buck converter? Go back to the equation. There's only one equation we looked into today. V0 is equal to Vg into D. What is the ratio of V0 to D? No. V0 is equal to Vg times D. And I want V0 by D. That is what I am looking at. And when frequencies are 0. When frequencies are 0, it means you are at steady state. And this is a steady state equation. What is the ratio of V0 by D? Vg. That's it. So this becomes Vg. You understand? Without actually solving the network, I am trying to derive the equation. Got it? Now what is omega naught? Omega naught is the frequency at which your LNC resonate. Is that clear? And obviously they have to be function of just LNC. There are no 2, 3 inductors, so it is 1 by root LC. Simple as that. Right? Similarly, Q is 1 by R root C by L. Simple as that. See, these are all. Why am I deriving something like this is a very complex network. Though you linearized it, getting results by solving this is a very tedious task. And what did I do is, without solving the network, I am trying to write the equations. This is how we do when you cannot analytically derive a network. It's very difficult, right? Let's say you have parallelly connected converters working at, very complex things that you look at. Then out of intuitions we write few things. We simplify it in our head and then write. Okay? So now if you look at the converter, I'm going to erase everything. we are looking at T. Now you know why the shape is like this. So the entire T, which is the hero of today's class, is, we have tried understanding him. T is now some constant K into Vg, which is also constant, divided by S by omega naught whole square. I will write it as uncompensated. Okay, plus S by Q into omega naught plus 1. So how does this guy look like? Is I am writing out of experience, because I know that a second order system will have a DC gain which is K into Vg, and then falls like this. And then why? And then this attenuation is called, this is minus 40 dB per decade attenuation, because the orders to, see, I know few general things. When S is equal to 1, the rate at which the loop falls is minus 20 dB per decade. There is a reason I can derive all of these things out of nothing, but then we have a lot of time constraints. So I am trying to give you few what you call tips. If S is equal to 2, it falls at minus 40 dB per decade. If S is equal to 3, it's minus 60 dB per decade. So this guy is falling at minus 40, and this point is called the resonant frequency, which is 1 by root LC. This is how it looks. You see, it has a DC, it has a resonant, and then falls. There is something else that is happening here. Don't have to worry too much about what is happening there. Okay. And if you look at the phase, okay, what I've drawn is not the magnitude, just the magnitude. It moves from 0 to minus 180 degrees. It actually falls like this. We will realize this in MATLAB. I'll show it to you. And at this point where you have the resonant, you have minus 90 degrees exactly. And this is omega. Okay, is it clear? This is how it looks. Now what I am supposed to do is multiply this with GC. Okay, now what you should do is you should look at this. Hey, look, whether is it okay for me? Am I providing sufficiently high, sufficiently high gain? Okay. Now there is something called as a crossover frequency. This loop crosses 0 dB at some line. There is a 0 dB line. Okay. This is a 0 dB line. Have you looked at the frequency response of amplifiers? It looks like this, right? And you define something called bandwidth. What is bandwidth? Bandwidth is the frequencies which you want to pass. Others you don't want passing. Here also the same thing. It's the same bandwidth. This decides the bandwidth. Now let's say the bandwidth is 1 kilohertz. What it means? That means less than 1 kilohertz of Vg. If the Vg variation, if the Vg has frequencies less than 1 kilohertz, I want to attenuate all of them. That's the reason why you have a very high loop gain there. If your bandwidth is very large, you are attenuating even more frequencies. If your bandwidth is much larger, you are attenuating even more frequencies. Now you should see, if I am setting at 1 kilohertz, whether 100 hertz is a good attenuation to me or not. So based on that, you should set your bandwidth. And there is also one more reason, bandwidth also decides bandwidth also decides your speed of with which you execute all of this. That's a different story. But you understand the importance of the loop. Is it clear? And I'm going to multiply GC to make sure I shape it the way I do. Because this is anyway fixed, this shape is fixed. If you want to alter the shape, you have to multiply with something, right? So what is that multiplying factor? It is not a constant. It is just something like this. What should you multiply so that you shape the loop is the design of controls. So this has some poles and zeros. Where will you place the poles and zeros so that you attenuate it? Okay, so that's the design. Let's look at the other things maybe as the time permits. Okay, fine. We have something called a phase margin test and all. We'll see it later. But our objective today should be to derive this. We should be able to plot this in our MATLAB. Thanks.
Thank you, Dr. Arjun. Today, when you started the session, you told it is very basic. but you taken is a very deep dive into the power electronics from the buck converter, how we can derive into two different configurations like voltage source converter and as well as boost converter. So I hope all the participants are very actively participating, like they are noting down the equations, and that's very nice, sir. So thanks you for being here. We are very happy to have you here. Now I request Dr. Pradeep Kumar Dixit sir, Head of the Department, Electrical and Electronic Engineering, to present a memento for the today's resource person, Dr. M. Arjun. Please. And he deserves a lot of applause because he derived that.
Thank you, sir.
Thank you, sir.
Thank you.
Now, followed by we have hands-on session in the computer lab from 4:30 to 5:30. Now, whatever sir discussed, so the group shaping. So we will have a practice on hands-on. Please join in the computer lab. Thank you.